Hello and welcome to another Geo-Institute live stream. My name is Christina Scott. I am the GI Technical Manager, and it's a pleasure for me to host today's live stream. Before we move to our presenter and moderator, I would like to give a few announcements about ASCE and Geo-Institute. For Geo-Institute, our new viewers who do not know who we are the Geo-Institute and we are part of the American Society of Civil Engineers. ASCE, the American Society of Civil Engineers, have 9 technical institute and 9 technical advanced divisions. If you want to know more about the technical institutes and divisions, please visit asce.org. If you want to know more about GI, who we are, please visit geo-institute.org. And in our website, you will find that we are a technical society with about 12,000 members, mostly geotechnical engineers, geologists, geophysics, and also soil technicians. We have chapters around the nation, and we also have board and technical committees. So if you want to know more about GI and the community, please visit our website. Since you are in our website, I would like to invite you to our student participation fund. Currently, we have a campaign. If you join the 96 Club, you can get the Raw Peg bobblehead. This is a limited edition item. So since we are in the giving month, you can visit. We have more items where you can get, and then you can give it to someone else. So you donate to our students and you can give a gift to your lovers. We will handle questions in our live chat. So please enter your questions anytime, and Luca will handle those questions or will answer those questions at the end of his presentations. If you like what you watched today, I just want to let you know, Maccaferri's been doing this with us for a long time. And a couple of weeks ago, Luca presented as well another live stream. The other one was about surface stabilization design for soil nail slopes. So I encourage everybody, after you watch today's live stream, to visit our YouTube channel and type Maccaferri, and you will find all the great content Maccaferri has been doing with us. Saying that, I don't think I'm missing anything else. I would like to introduce all the way from Golden, Colorado, Mark Vaselli, Principal Geotechnical Engineer at BGC Engineer. Mark, if you're ready, the floor is yours.
All right, thank you, Christina. So yes, I'll be your moderator today, and we're going to start off the first hour with a presentation from Lucas Martins, who's a technical specialist for geohazards with Maccaferri in North America. And at the end of his presentation, we will open it up for questions, and you'll see me again there. Lucas, I'll turn it over to you.
Well, thank you, Mark. Thank you, Christina. Thank you, everybody that's attending here today. It's a great Thursday, so let's go ahead and start this. As Christina mentioned, this is something that we have been doing for a while here with Geo-Institute. Last year, we held 3 webinars with different subjects throughout the geohazard mitigation. We had a webinar on simple drapery, one for pin drapery and soil nails, and one for rockfall barriers and attenuators. All those webinars are still available at the at the Geo-Institute YouTube and are ready to be watched. The first webinar has a lot to do with the presentation here today, so I suggest you watching that. Also, as Christina mentioned, on October, we held a presentation on soil nail slopes, on soil nail design, and that is also available. Today, we're going to be covering the macro design software for drapery systems. I'd like to point out that all of Maccaferri will provide PDHs for all of those presentations. There's a QR code on the end of the presentation. If you scan that and request a PDH, we will reach out with that. First, for those that are not familiar with Maccaferri, Maccaferri started 130 years ago in Italy by the river Reno with the first ever gabion application. So it was a river failure with causing major flood, so they did a weir with gabions. Since then, they developed multiple other applications and improved on their systems, the biggest improvement being the double twist wire mesh. That's what Maccaferri is known for in gabions, in erosion control, in rockfall protection. The double twist was very revolutionary because by introducing that second twist, it creates redundancy on those connections, so it creates a non-raveling pattern on that mesh. This is still the pattern that Maccaferri uses for all of their sectors that they apply. So Maccaferri is present in multiple different sectors as MSC walls, gabion walls, erosion control. But the focus today will be on rockfall draperies, simple and pin draperies. This is an introduction to the software, like the Macro Design software. The Macro is a free web-based design software developed by Maccaferri. It includes both tools for simple drapery, which we call the Macro 2, and the tools for pin drapery, which we include on Macro 1. It allows engineers to evaluate, configure, and optimize rockfall protection systems with standardized methodologies. Again, it's a free software available online. You just access the website and do it. We will start on the simple drapery module, and we'll be covering an introduction to the solution, the design procedure, and also go over a live software demonstration, if my internet allows for it. Our design framework draws heavily from established literature. For those who'd like to dive a little bit deeper into the analytical background of the design method, these are some of the main references behind this first module of today's discussion. First, we have the analysis and design of wire mesh cable net slope protection. This is a paper developed by the Washington State Department of Transportation, and this is a very heavy paper on designing simple draperies. Second, we have the book, Rockfall Characterization and Control. This also covers a lot of the simple drapery design. So what it is? So simple drapery is designed to control and guide rockfall into a safe catchment area. It doesn't stop the rocks where they detach. It simply manages that fall path. One of the key advantages of this system is that it's cost-effective and relatively quick to install. It is suitable for slopes where we expect the rock detachment, but there's no need for a full stabilization of the slope. In other words, the slope doesn't require any kind of reinforcement, just containment. From a design standpoint, there are a few key points to keep in mind. First, the drapery must extend above the rock source, so it actually captures the material. It also, the anchor spacing and layout is critical because besides maintaining the alignment of that mesh, it also determines the performance of the drapery. And remember that the mesh carries its load mainly on the longitudinal direction, up and down, which makes the mesh tensile strength one of the most important specifications. Finally, the mesh unit weight plays a significant role in dampening that rock movement. A heavier mesh will push back that rock with a higher load. There's also limitations to this system. A simple drapery is not suitable for actively moving slopes or unstable slopes. It provides no tensile resistance or structural support on that slope. In areas where a lot of loose material is expected, it may require frequent cleanup to keep that catchment functioning properly. With this introduction in mind, let's move into how the system is modeled. Here you can see the overall concept. At the crest of the slope, we start with the top anchors, which are installed in a regular spacing. These anchors are responsible for transferring the loads back into the stable mass, or stable rock mass, and secure that top horizontal cable. That top horizontal cable runs along the crest of the slope or above the crest of the slope, and the cable supports the mesh as it hangs down the face. Those top anchors can either be intermediate anchors or lateral anchors. As the mesh transfers load into the top cable, the cable redirects those loads as a tension into those anchors, following the behavior described by a catenary theorem. For the intermediate anchors, the lateral components of this cable tension cancel out. So these anchors carry significantly lower loads compared to the lateral anchors, which resist the full horizontal pull of this system. As we mentioned, simple draperies require a safe catchment area. This can be a ditch, a rockfall barrier, or an embankment. But what happens in situations, especially when there's no space for a catchment ditch at the toe of the slope? For those situations, we can use something called a closed toe setup, in contrast with the open toe setup. Instead of allowing the debris to fall freely and accumulate on a safe area below, a bottom cable is installed and anchored along the base of the mesh. This bottom cable contains the falling material and creates sort of a pocket that traps debris behind the mesh. It is effective for protecting roads or infrastructure directly below the slope, but it comes with a significant trade-off where debris now accumulate at the bottom and the buildup requires periodic maintenance to avoid overloading that system. Needless to say that in a closed-toe configuration, the loads impaired into the system are significantly higher, so you expect a more robust structure. When it comes to designing these systems, I've come across many projects, and perhaps you have too, that the design of those simple drapery systems are often oversimplified using like rules of thumbs or empirical standards. It is not hard to see why though, because empirical methods are quick, familiar, and have worked reasonably well for years. But that can come at a cost of precision and optimization. Those empirical approaches often ignore key variables like debris load, slope angle, top cable strain, or snow loading, which can result in either an over or under design system, which will, in the end, either cost money or safety. But what is often overlooked is how simple it actually is to perform this basic drapery design. With a clear calculation steps, we can go over from guesswork to like engineering and confidence in minutes. My goal today is to show how straightforward and impactful a proper calculation can be for even so-called simple drapery. Using a basic limit equilibrium model, the system is analyzed by balancing the resisting forces against the driving forces to calculate a safety factor. On the resisting side, we have the tensile strength of the mesh and the resistance of the anchors, both which oppose the driving loads. For that, we have the weight of the mesh, we have any accumulated rock or debris within the system, and in some regions, the weight of the snow and ice buildup. So the tensile strength of the mesh. Again, I said that it primarily functions along its longitudinal direction. So the tensile capacity is a critical design parameter. The photos and the diagrams here show a standardized test setup used to measure that longitudinal tensile strength of the mesh. The mesh is clamped and loaded until failure. For example, our steel grade HR30, a common used drapery mesh, has a nominal tensile strength of 12,000 pounds per foot, and it breaks at an elongation of about 6%. This strength value can be directly plugged into the limit equilibrium model, but its elongation is an important design consideration that's usually overlooked. It's overlooked because the model assumes that under load, the top horizontal is uniformly loaded and the wire mesh is uniformly tensioned. But in reality, the mesh undergoes a non-uniform deformation. And as it adapts to the slope geometry and transfer the load, rather than transferring the load evenly, a mesh with a large elongation will create pockets of concentrated tensile force, which can be especially damaging when debris accumulates at the bottom. This is an effect that is addressed on the WashDOT guidelines, and it suggests that the introduction of vertical high-strength steel cables into these systems, either woven into the mesh or connected to it, will help control deformation under load and allow the system to mobilize the full tensile strength capacity of the mesh. And here is where I present you the steel grade HR. Steel grade HR is a composite cable mesh, meaning that you're introducing tensioned cables into a wire mesh matrix. The cables create a high strength with low elongation mesh. The nomenclature here refers to the distance in between those cables in centimeters. So a steel grid HR30 has a spacing of 12 inches, and a steel grid HR50 of 50 inches. The closest together those cables are, the higher the strength of the mesh. Here are some photos of the steel grid HR on some projects. Here is a Big Stone Gap with Virginia DOT. Here is a Waltham High School in Waltham, Massachusetts. I-80 job in New Jersey. The next resisting element on the drapery system is the anchors. While the mesh carries its load longitudinally, the anchors are what ultimately connects the entire system back into the stable slope. In a simple drapery, the anchors are typically one of two types. Solid steel bars, like the one in the photo, which will resist that load primarily in shear, as shown in the photo, or flexible cable anchors, which are loaded in tension. From a design standpoint, there's no technical performance difference between the two. Both adequately transfer the load. In most projects, the choice simply comes down to contractor preference. Now we move to the first driving force, and it's the self-weight of the mesh, labeled WM on that diagram. A simple formula is the mesh unit area times the length along the slope, which gives you a mesh weight load per foot. Next, the next major driving force is the weight of the rocks and debris. As material accumulates behind the mesh, its weight adds a vertical load to the system. Those images show how significant that buildup can be, from fine fragments to large boulders. And it directly increases the demand on both the top cable mesh and anchors. To estimate this debris load per foot, we calculate the volume of accumulated rock behind the mesh and distribute that over an anchor spacing. This gives us the debris acting along the slope. This also can be dimensioned as a height and width of debris. A different approach to calculate that, and one that it's a little bit more clear, is whenever you have a number of boulders that you want to allow to accumulate, or a number of rocks, in between an anchor spacing. So you can divide that volume of rocks for the anchor spacing, and then you'd have a load per meter or per feet. Now, this input of debris accumulation, it's very clear whenever you have a closed toe configuration and you know the size of pockets that you want to allow to build up, but it's less clear whenever you have open toe drapery. Theoretically, there would be no accumulation, but in reality, it is important to consider the concavities and convexities of your slope to account for debris accumulation throughout the face. Although the volume here would be much less than a closed toe configuration, there would still be the need to account for a certain amount of accumulation. Here's a photo of a project, that's an open-toed project, where there is some ledges where the material is accumulating. In colder climates, snow and ice can add significant load to drapery systems. Snow typically accumulates on slopes shallower than 65 degrees, but ice, as you can see on the image, can form and bond in much steeper spaces. When it builds up behind the mesh, it contributes to that vertical load just like debris. When that equilibrium is set, now we identify the resisting forces that we need to account for those loads. Once those loads are determined, the results will guide us through 3 key safety checks. First, we got to verify the anchors. Are they strong enough to resist the shear or tensile? And is their embedment adequate for resisting the pull-out? Then we check the mesh. Is the mesh has enough tensile strength to resist that load? But beyond the strength, durability is also a critical design input for the mesh, for our long-term performance of the mesh, especially in aggressive environments like roadside and marine settings. This chart here shows how different coatings degrade over time. While standard zinc or zinc aluminum may meet short-term design life for aggressive environments, a zinc aluminum plus polymac coatings offer significantly extended durability, over 120 years. That makes it ideal for long life applications. The final check is the support cable. Based on that sag and span, we calculate the horizontal tension required to support the mesh and those variable loads. And the diagram shows a typical configuration where small vertical loads can generate large tensile forces due to that shallow sag angle. A cable with a sufficient diameter that provides a sufficient break strength should be used. And this kind of ends our design here. So even for simple draperies, precision do matter and site conditions will vary. So we should take this design and use a tool like Macro to do this design. I'm going to go ahead and run a live calculation here just to show how simple that is. So if you go in and type in edesign.maccaferri.com, you're going to have access to all of our design softwares. This is a web page where you can register and have access to them. On the bottom here, you would see the MacASCE, just the soil nail design that we presented last. And here is the drapery design that we're going to go over. As we enter the application, we would create a new project. For example, I have some saved here, but this would be the simple drapery one. You can create a project number, owner, design firm. For the country, you would probably want to select United States or Canada, whatever you're based out. You can also enter the location of your project. Here, I want to enter the location of our headquarters, which is in Hagerstown, Maryland. All of our materials are Buy America, meet Buy American, and are fabricated in the U.S. So just pointing that out here. Okay, so as we create the new project, it's going to ask what module do I want to use. Do I want to use Macro 1 for pin draperies, which we'll cover next, or Macro 2 for simple draperies? Once you click next, it's going to ask you between metric and imperial systems. So this is the software itself. On the top, you have some options like saving the file to your computer. Here you have your account name. Under help, very important, you have the user guides, the user and reference guide. The user guide goes through the inputs, and the reference guides go through the background design. So those can be easily accessible through here. So let's go ahead and start doing our rock slope. I have here my cheat sheet. So let's start with the slope that's 75 degrees. and about 80 feet high. We are going to consider a material accumulation of 4 feet by 4 feet. That means that the debris accumulation is going to have those dimensions. I'm going to show a little trick later on how to verify if this is appropriate or not. For the friction angle, the debris friction angle should be entered as about 75% of the residual rock friction angle, and the debris unit weight would be also 75% of the intact rock unit weight. For this, I'm going to leave 125 PCF and 25 degrees. Now here we have a parameter that's a little trickier. Friction angle between mesh and slope. This friction angle has to do with the undulation and asperity of your slope against the mesh. This input is more sensitive in applications where you have snow weight on top of that mesh that creates a bigger friction load. This comes straight out of the Washington guidelines. And if we go down here, you see that you have a few photos as guiding you. So you would use an angle between 18 and 35 for a flat slope, 36 and 59 for a wavy slope, and above 60 for a very rough slope. If you want to dive a little bit deeper into this, you can go into the WashDOT guidelines and they explain it a little longer. But for a sake of time, let's go here and enter a flat slope. So very little resistance against that slope. Here's where you'd consider snow accumulation if you want a snow or ice thickness on top of your mesh. For the site environmental level, this is a European norm, but it kind of gives you an idea. For different sites, for different environmental levels, you have different corrosion requirements. Here on extremely aggressive, you'd only be considering something with a polymer coating. For the mesh itself, we have the multiple options of mesh that Maccaferri offers. We always recommend getting in contact with us to take to see what is available in the North American market. But as we mentioned, Steel Grid HR is the mesh with cables in one direction, and the number would be the distance in between those cables. And here you have the double twist, which will be the wire mesh without cables. So let's go with a PMC coated Steel Grid HR50. Now we come to the anchoraging. First, we enter the anchor spacing and the wire rope diameter here. So let's enter a 3/4 inch wire rope on the top. For the crest anchor, here are some preloaded options. You can also create a custom one. But let's go with a grade 75 all threaded bar, a number 8 or 1 inch with a 3-inch diameter hole. You can consider for corrosion crown or not. Now the bond strength. The bond strength is a value that can come from a site test or from the literature. If you click on the little I, it gives you a little cheat sheet here for some bond strength, grout adhesions, bond strength for certain types of rock. Let's enter the granite and basalt one. Plasticization. This is also something that has to do with the site. It is the shear band size. Here are some plasticization values that you could use. But let's leave at about 10 centimeters. And then you enter your safety coefficients. Those would modify the loads or the resisting factors. So here you have a safety coefficient of 1.5 on those variable debris loads. If you click here, you're going to have some codes, European codes. Safety coefficients on the permanent loads, that would be the mesh weight. Here you have a safety reduction on the mesh resistance. This will reduce the mesh tensile resistance. And it is a 2.5 in order to consider the differences between a real life scenario and the test. As you saw, the clamping, the simple test. You have the geometry of the top longitudinal cable. This is a safety reduction for slopes where you have a very undulated crest and you can't guarantee that your anchor spacing is going to be this the 10-foot, for example, on this one that we entered. So it would be 1 for regular slopes, and then 1.1 for irregular slopes. Here you have a strength reduction on your cable, a reduction on your bar yield stress, and a reduction on that grout bond strength. All of those, if you click on the little E, there's an information. Let's go ahead and run and show you how it looks. Once you run, you're going to have those 3 checks that I covered: the mesh check, the top cable check, and the anchorage, the intermediate one, and the lateral anchorage check. Because we entered the safety factors beforehand, we're shooting for above 1 safety factors on the end. If you scroll down, you're going to have all of the calculations cleared out here for you. First, you'd have that design load. You have the total stress, the admission tensile resistance of the mesh, the debris load, snow load, mesh total load. You have your cable design with the maximum force on the cable, the maximum working load of the cable, maximum sag in between those 2 anchors. You have your anchorage calculation. And I want to point out a few things. So you saw that we did the design with a thread bar anchor, but I mentioned you can use cable anchors as well. So if I have a thread bar anchor design and I want to use a cable anchor, the tensile resistance of your cable anchor has to match the shear resistance of your bar. So that's what is showing here. Minimum required tensile strength of cable anchors, 25 kips. That's the same as the maximum force of lateral anchors. So the maximum force of lateral anchors has to match the tensile resistance of your cable anchors. So if you want to pick from a cable anchor, you can go to a technical data sheet like this one and pick the diameter of your cable anchors. For example, a 5/8 inch cable anchor has a minimum break strength of 54 kips. So that would be appropriate for a 24 kip load. Here, the same for the intermediate anchor design. You have that force here for the intermediate anchor. Now, I said that there was a trick that I was going to show with the debris load. And this is the trick here. So you see here that you have the debris load equals to 1,292, so about 1,300 pounds per foot. And our anchor spacing is 10 foot. So if you multiply that debris load by your anchor spacing, it means that you're accounting for about 12,000 pounds of rock between your anchor spacing. Now, if you consider that a 2-foot diameter rock weighs about 720 pounds, that means that you're accounting for a certain number of boulders. So this is an easy check to see if your debris load is appropriate or not. I know that using height and width is not the clearest, but that's how the methodology describes, but that's the trick that I use. So yeah, this is the design. You can export a PDF with your design. As you open it, you're going to see there's a very pretty looking report here with all of those parameters. So that kind of concludes us on our simple drapery design. As you can see, it was a very fast design, very fast calculations. You can optimize that system very well, choosing the correct cable diameter, the correct anchor spacing, the correct mesh to adequately take in consideration all your site conditions. So now that we covered the macro 2 for simple draperies, let's jump into the macro 1 for pin draperies. Although very similar in name and involve the same elements of a simple drapery, it has mesh, anchors, cable. The goal and the design of pin draperies is very much different. For this module, we design based on those methodologies. Again, for those who want to dive deeper into the design of those systems, those are some papers that I recommend. Here you have a paper from 1988 on hexagonal wire mesh for rockfall and slope stabilization. Very good paper for the beginnings of rockfall draperies. Next, we have the deformability of the rocks and the rock joints. So this is going to come in place on the spin drapery. We're going to cover that. Next, we have that Rockfall book that I already mentioned, the TRB book. Covers everything about rockfall. And last but not least, if you have time to see one of those papers, this is a paper that you got to see. It's a very in-depth analysis of multiple different drapery nets and cable nets on a pin draper scenario. They even have a full-scale test on a pin drapery, which is very, very interesting to see. So the pin drapery is designed to stabilize and retain the rockfall or the loose superficial rock, and it uses a regular pattern of fully grouted passive anchors that pull the mesh tight against the slope, improving that near surface stability and reducing the likelihood of block detachment. One of the main advantages of the systems is that it requires minimum to no maintenance once installed. And unlike the simple drapery, it doesn't require a catchment area. So it's suitable for locations where the space is limited and where debris must be prevented from detaching altogether. From a design perspective, the mesh still has to extend above the source zone, and the anchor spacing and layout here is critical to ensure the conformity of the mesh to the slope. In this type of system, the mesh now is loaded on an out-of-plane direction. So the mesh punch strength is the key mesh specification. The stiffness is a concept that we will cover, and it is essential on the performance of those meshes and their ability to contain that rock movement. Now, it sounds too good to be true. What are the limitations? Again, with all good solutions, is cost intensive. Installation on those types of systems, the price for installation is directly correlated to the amount of anchor drillings that you have to do. Drilling is the driving cost. In a pin drapery, you have more drilling than a simple drapery, so it will be more cost intensive. To start the design, we first need to identify the superficial unstable portion of that rock mass. This portion can be identified as joints, weakened rock pockets, or boulders fit against each other. Once you identified that unstable rock mass, it's easy to identify the slope inclination, the thickness of that rock mass, which is parallel to the slope. And also we need to identify the inclination of the joints that are dipping on an unfavorable way, which here we have that most unfavorable joint and the angle alpha. That is the sliding joint or sliding plane for that rock mass. The driving force here has to overcome that dilatancy of the joint. So basically you have the joint resisting that movement. In this stage we call it a prick resistance. But when that maximum opening of the joint is reached, the rupture and the asperity starts and the sliding movement gets faster. So then we have what we call the residual resistance. As you can see, those are rock mass characteristics. So it's joints, discontinuities. It's different than the presentation that we did earlier this month on soil conditions, which you would use a cohesion or soil friction angle. So we are characterizing the failure here with discontinuities, an amount of mass that the anchor has to resist, and a sliding joint where that mass slides. On the top left corner here, you can see that an anchor that's placed through a rock mass can be subjected to a wide range of stresses. This can be a pure pull-out stress, like in situation B here, or a pure shear stress, as in situation E. So now we have a characterized rock mass that has dimensions IX, IY, which is equals to your anchor spacing, and thickness S, which is sliding over that unfavored joint. And we can design a structure that will resist that movement. So the anchors here play this leading role in providing the stabilization of the rock mass. But the mesh provides that superficial stabilization by resisting movement and keeping the rock from detaching in between those anchors. Stabilization is offered through passive resistance, meaning that the mesh strength is only mobilized after deformation attributed to that loading happens from the loose rock to the mesh. So the mesh will only push back on the rock if the rock pushes onto it. Therefore, here it becomes clear, and it's shown that it's very important that the steel wire mesh facing is able to mobilize its high strength at low elongations to provide the stabilization to those loose rock surface. So the performance of the mesh is determined by its stiffness or the mobilization of its punch strength under load. I say that because different materials have different behaviors under a same applied punch load. On the photo on the right, from top to bottom, you notice the increase in deformation that can occur, and depending upon the product. The product on the bottom is made from a high-strength steel wire, yet the manufactured mesh provides the highest deformation as compared to the first and second product. Therefore, it's not just the component of the mesh, but the method of manufacturing that gives the mesh its characteristics and will determine its ability to mobilize its strength under load and ultimately provide stabilization to the slope. The point is that a serviceability failure may occur when the design is based solely on the ultimate capacity of the mesh. This happens when an amount of material that is impacting the anchors is different from the design parameters. At that point, you can see here on the photo that the amount of material accumulated on top of those anchors is higher than the design. You had a washing on this top anchor and an overloading on this bottom anchor. That's because the mesh allowed for a certain amount of deformation where it created a void that has to be filled with the material from above. We call that a serviceability failure. So anchors play the leading role in superficial stabilization, while the mesh holds back the blocks in between those anchors. That brings us to our cable net, or our composite cable net. The system incorporates a net or a grid of pre-tension high steel cables that provides a very high strength with a peak strength mobilized under very low elongation. So those cables are inserted into the mesh under tension. So as soon as you tug on them, they're going to tug back. For the most demanding pin drapery applications, Maccaferri offers the Mac Armor, or commonly known as Rock Mesh line of products, which have two cables interwoven into the mesh into a one-layer system. The cables are in both directional here, longitudinal and lateral directions, which provides the greatest punch and puncturing resistance available in the industry. For example here, the Rock Mesh 3030 or Mac Armor 3030 has cables on a grid pattern of 1 foot by 1 foot, or 30 centimeters by 30 centimeters. So a quick trick here for the Maccaferri product, if you see two numbers, it's probably a biaxial grid. If you see one number, it's probably a uniaxial grid like the steel grid. So this was quicker than the simple drapery, but it's basically you're trying to prevent a rock mass from moving. So you characterize your rock mass, your size of your rock mass, and you're creating a netting that will prevent that. As you jump into software here, we're going to see how that is done. Okay, so coming back to the software, we were here at the Simple Drapery module. So let's go back to the hub and add a new project. So this is going to be our pin drapery. Let's go ahead and add the US. That's the location. Go ahead and enter the same one. 0.22. Okay. Now here, as we select, we have to select the module Macro 1 for reinforced systems and choose our imperial systems. So first you have the characterization of that rock slope. Here you have the inclination of the slope. So let's enter a steep slope. Here you have that parameter, thickness of the superficial instability. This is that area where your slope becomes not unstable boulders or rocks, but it's more stable back. This is a key parameter here, and probably the hardest one to come up with. After you do your borings, that's going to be a little easier. Here you enter the density of your rock. You can also click here for different unit weights. Here you have that joint. Here you have the dip, compressive strength, and roughness characteristics of that joint. Most of the times the information is not present. We would love them to be present. So if you want to enter parameters to consider general compressive strength for joints in different types of rocks, you can click here, or you can leave at 10.5 as minimum parameters here for that strength. Dip, also a parameter that we would love to have, but not always something it's present. You can leave at 25 or 25 to 45 for the most conservative calculations. For this system, since it provides stability to the slope, you want to enter your seismic coefficients. On external forces, if you want to account for ice buildup or snow buildup, you can do that. It would create a shear force here on the nails or on the anchors. Again, for that environmental level, for the corrosion protection. Now you have the characteristics of your anchor bar. It's very similar to the simple draper, but now you have horizontal and vertical spacings. So let's go ahead and try with a 10-foot by 10-foot pattern. Here you have the inclination of your bar to the horizontal. Again, I showed that the bar, depending on the inclination, can act in shear or it can act in tensile. So here you want to always shoot for a tensile resistance. You can enter some kind of coefficients to increase the anchor drilling diameter or leave it at 1 for no increment here. For the anchor type, again, we usually use threaded bar. It can be hollow bar or steel bar. If you want to use a hollow bar, you can enter as custom. But let's go ahead and enter a grade 75, number 8 bar with a drilling diameter of 3 inches. Corrosion thickness, bond strength, same parameters that we see on the simple draper. This will calculate the anchor embedment. The plasticization, that's the shear band length. You can have values here too. Then we have the mesh selection. So we have multiple mesh selections. Here is that rock mesh or Mac armor. You have the 30-30, which is a grade of 30 by 30 centimeters or 1 foot by 1 foot. For the safety coefficients, here you can enter a custom safety coefficient and just enter a factor of applying on that stabilizing forces and a custom one for your driving forces. Or you can play around with the different coefficients here. Here you have the Uncertainty of the thickness. So I said the thickness is hard to guess. So here is where you would enter a safety factor to keep you safe there. So you have a geomechanical survey or a rough or visual estimation. For the uncertainty of the rock mass weight, you have homogeneous slopes or non-homogeneous slopes, so you can enter that here. Uncertainty of the rock behavior and weathering. So for compact rocks or weathering rocks, you have different parameters. If you have a question, what value should I enter here? If you go on the user guide and open it, there is going to be the parameters for the safety factors on the end, and it goes through all of the different parameters here. So it plays here between 1.2, 1.3, 1 and 1.5, and 1 and 1.5. So very easy here to access. Now we have our safety factors affecting the driving forces, the slope surface morphology, some external loads. Okay. Here is the coefficient applied to the tensile and punching resistance of that mesh. You have the coefficients reducing the strength of your bar and the coefficients on that bond strength. As we run the design, there's two checks. You're going to have the check of the sliding zone. This is more of an anchor check. So you have your anchor working ratio. So this is how much of the anchor is being utilized based on its maximum strength. And here you have your mesh working ratio. So for example, for this here, you can see that the mesh is being underutilized because we chose a very strong material. We chose Rock Mesh 3030 or Mac Armor 3030, pretty much our strongest material. As you go here in anchor bar, we can then try to increase this anchor spacing. So let's try to increase to 13 by 13 feet and run that. So you can see you can do different iterations to kind of better utilize the mesh. You can see after we enter that, now the anchor is fixed. So we might have to increase the diameter of that bar to grab a stronger bar. So you can play with the different elements and achieve different results for the same slope. Again, anchor spacing is very important here because, as I said, drilling costs a lot of money. So if you can increase your anchor spacing, you can reduce a lot of drilling and reduce a lot of money by using a stronger and stiffer mesh. On the result, you're going to see here that there is the force on that slip plane, and you have the stabilizing versus the stabilizing forces versus the destabilizing forces, or acting forces versus resisting forces. Here is the anchor safety factor calculation. You do have a minimum length of the anchor calculation, so that would be your anchor embedment. So that is calculated here for you. This is also calculated on the simple drapery. I didn't point out, but it also calculated. And on the mesh design, a cool thing here that I wanted to point out is you have your nominal displacement calculated. So if you think about it, as you're testing those meshes, you have that stiffness curve. You have, like, as you load it, the amount of elongation that it's going to respond with. So considering the force here being punch resistance of the mesh, punch force acting, so the 10 kips of force acting on that mesh, you expect a 3-foot elongation on the center of that anchor spacing. So this here is a key result if you're placing your pin mesh very close to your protecting structure. So if you have a building that's very close to your pin mesh and you don't want to allow that elongation to affect that structure, here's where that parameter would come from. So once you print out, you can go ahead and export the PDF. I'll open here and it shows you it's very similar to the other one, but the different results. Okay, and with that, it concludes our presentation today. Just under an hour. That's great. Here is that QR code for the PDHs that I mentioned on the beginning of the presentation. I suggest you going into our website and checking out some of the case studies that we have for simple and pin draperies throughout the U.S. if you need to contact us or contact me for any reason, if you missed something on the live demonstration and you want to go over it again, or you tried and you found something is not working correctly, you can send me an email or through the QR code as well, and we can get in touch. I appreciate everybody keeping their attention and being engaged throughout the presentation. Now, if there's any questions, I'm happy to answer.
Yeah, thank you, Lucas. So again, we're going to take about 15, 20 minutes here to go through questions as they come up. We've already had a few come in, and I'd encourage others to go ahead and type them in, and we will relay these to Lucas. So Lucas, one of the first questions that comes in here is during the pin discussion, and it has to do with what is the dimension for the top anchors on these draperies when driven into stable soil. So I'm assuming length and anchor parameters.
Okay, so that's for pinned drapery applications or for simple drapery applications?
Yeah, go for both.
Okay, so that is a key thing here. The macro is a rock slope stabilization. So our previous presentation, I do encourage people who are watching this to watch our previous presentation, which is a soil slope stabilization. So on the soil slope stabilization, you're pinning those anchors against soil. On the rock slope stabilization, you're pinning those anchors against rock. It's an important distinction here because a rock slope fail different than a soil slope. While the soil slope fails in a more fluidic manner, the rock slopes fail in a more blocky or more like through that discontinuity families. So through that stereo net analysis, so toppling, wedging, planar ways. So that's how a rock slope fails. So we disencourage people using a rock slope design program for its designing of soil slope, and using a soil slope design program to design a rock slope. So that's why we have two different softwares here at Maccaferri. So I do encourage you going to the soil. If you do insist on using it, a way that you can do is whenever you had that bond strength of the anchor against the grout bond strength, instead of entering a rock bond strength, you'd enter your soil bond strength, which is much lower than the rock bond strength. But those are values that you can find on the circular number 7 from FHWA, for example.
Okay, thank you. Mm-hmm. A question I have in regards to this, because a lot of times when you're doing this, you're putting it on a new slope, and so you don't necessarily know what debris loading or loading kind of conditions you might need to assume. So I was curious how what's your thoughts on the approach for verifying the debris loads or establishing those when you really don't have any historical data?
Mm-hmm. Yeah, so like for example, on the simple drapery, we saw that closed toe configuration. And that's when the debris loading really matters. So that's when you're accounting for a significant amount of debris loading. So that debris loading actually becomes the limit of maintenance of your system. So if on the design, for example, you accounted for a pocket of, for example, as we did, of 4 feet by 4 feet, so you're talking about that 1,300 or 13,000 pounds between your anchors, you can translate that into a volume. So that can be for the specifier, the designer that's specifying a system, that can be their limit for maintenance. So it says like, whenever you're getting close to that, you got to detach that bottom cable, clean it out, because that's your limit of your system. That becomes a little less important for the drapery design on the open toe configuration. That impacts more on the catchment ditch, for example. So you're going to design a catchment ditch that's going to require, that's going to account for a certain amount of debris. And that's also going to be your limiting factor for cleanup on that ditch. So once you start going over that volume on that ditch, you got to go ahead and clean it up. So it kind of, you use your max debris loading from the design as the limits of maintenance of your system, if that makes sense. But that's how we do it.
All right. No, that sounds good. So a question that just came in here is, do the uncertainty coefficients assume that the conditions have been assessed by an experienced engineer?
That's a great question. I hope it did. Usually, before you come to a pin drapery design, you have a geostructural or a geotechnical or a geological report performed on a slope. So you'd have borings, you'd have mapping of your discontinuities, you'd have your stereo net analysis to determine what kind of failure you're looking at, toppling, wedging, or planar. From that, hopefully you'd have an analysis like a dips analysis where you can actually find what is the amount of material. So hopefully you have that information before. So those uncertainties are for you to play around if you're not trusting that geotechnical or geological report was done correctly. Or sometimes you have to do something in a hurry as a preliminary design, so you account for more certainties, and as you're getting more information, you can reduce those uncertainties, as in like a lot of different designs.
Yeah, so kind of one of those it depends type answers where hopefully you do have a good assessment that you're working from.
I mean, all of us engineers love safety factors, right? So yeah. That's your safety factors.
Yeah, well said. And another question I know that comes up around these a lot has to do with both the topics of corrosion resistance. Sorry. So methods like galvanization or coated mesh, I know, is talked a lot about, and then that rolls up into the life cycle needs or assumptions. Some uses, like say in a mine where it might be a shorter lifespan type of project of say less than 20 years, they might have different needs around corrosion, whereas say a highway department might be looking for a longer term, maybe even almost like an in perpetuity type of lifespan. So do you want to talk any on how to determine maybe what types of corrosion resistance might be needed in the design, and then also maybe some comments on the lifespan assumptions that go along with these systems?
Mm-hmm. No, that is a great question, because it's a question, as you said, we get often whenever we're dealing with those systems is how long can I expect this to work? And there are two factors that really affect the lifespan on those types of applications. One is your maintenance schedule. It really affects having that visual survey, visual inspection of that system throughout time to assess if the debris loads are under the design load. So that's one of the key factors that affect the lifetime. But another factor that we can control is the coating protection. So assessing correctly your environment is very important. So assessing if there is going to be ocean spray, assessing if you're right beside of a road and you have now salt from the winter months that's being sprayed on that mesh. So the corrosion protection is a factor that you can choose. When it comes to corrosion protection, you basically have 4 options across all the product lines of the different manufacturers. You have basic galvanization, which would be basic zinc. You have Galfan, which is zinc aluminum. You have a polymer coated mesh, and you have stainless steel mesh. Stainless steel mesh is very expensive. Very, very expensive, so it's not even on this chart for that reason. But the amount of corrosion protection per unit area of the mesh is also important, because the way that the corrosion protection works is it is losing its coating through time instead of losing steel. So that is also a key point here. So you can see that Maccaferri products can allow, because we have more steel in our products, we can allow for a larger amount of galvan or galvanization. So once you have assessed correctly the aggressiveness of your environment, if you have a very aggressive environment, a low aggressive environment, temporary application, you can correctly choose your coating requirement from that. I do point out here this PMC coating. So what is PMC coating? So back in the day, I'd say like 10 years ago, the meshes were starting to get coated with PVC or the polyvinyl. So that has some issues with abrasion, with UV stableness. So what Maccaferri does is, after seeing the issues with PVC, it developed a polymer that we call a Polymac now, which is way superior than PVC for abrasion, UV resistance, and for lifetime expectancy. So it's a heavily tested polymer, and the abrasion tests are showing 120 years of abrasion to remove that coating, that polymer coating. This is also environmentally tested. So it's also something that is tested through, I think, the University of Colorado, if I'm not wrong, on that environmental effects. And so that's also something known for the PMC. So again, the right choice of coating, very important here. I don't know of a US norm, but the European norm on this, on the aggressiveness here, I think is the 1023 European norm, is very good to help with that.
Okay. So Lucas, we have a couple more questions here. That was a good answer on the lifespan and corrosion aspects there. This next question is a little more on the technical side. Give an example of what is the suggested pressure of the debris on the elongation mesh in units per square inch or cubic foot on the rock slope and on a soil slope, or I guess making a comparison between when you're looking at this on a rock slope versus a soil slope.
Let me try to understand the question here. So it's comparing what kind of load requirement from a rock slope to a soil slope, if that's kind of what I
I think that might be a good one. The question, asks about it in
a pressure, like a
pressure, right?
A pressure, yeah.
But yeah, no, maybe just to start with the rock and soil and go from there.
Yeah, you definitely for soil slopes using wire mesh, usually you're talking of slopes up to 70 degrees and a thickness less, like a shallower thickness of instability. So whenever you're talking about a rock slope, you're expecting a lot higher pressures into your mesh than a soil slopes. There are other parameters that are important on the mesh for a soil slopes, but we definitely see a larger requirement of punch strength or pressure for the rock slopes than for the soil slopes. But you also are going into larger anchor spacings. So what I said about deformation, limiting deformation, is a lot more important on soil slopes than rock slopes. So on a rock slope, you're talking about 10, 12 foot anchor spacing. On the soil slopes, you're talking about 5, 8 foot anchor spacings. So even the amount of material that you're trying to hold back is different.
Yeah.
So
okay. That's a good transition here, maybe to our last question. We've got about 5 minutes to go here, but is on the detensioning or retensioning procedures and the design details associated with a closed toe drapery. Is there any kind of special connections required, or yeah, what's the Maccaferri thoughts on that?
No, that is, whoever asked that question, know those systems, because that is a key component there that I did not mention and forgot to mention on my presentation. But on closed toes, a key aspect whenever you're designing those systems is to remember that every so often you will have to detach that cable to allow the material to freely fall so you can clean it up. Or else the material is going to start building up, it's going to fail. So there are two ways of doing this. So if you're using thread bar anchors, you're going to have your plate holding back that cable. So you're going to back up your nut, take off your plate, and do it. That is way more complicated than whenever you're using cable anchors, because whenever you're using cable anchors, what is usually done is you add a shackle on that connection point, and all you have to do is unscrew that shackle, take that out, and then that cable comes open. So you're basically not really retensioning your cable, you're basically unconnecting it and connecting back together. But that is kind of the procedure. So it depends on the type of anchor you're using, but that is the procedure. Those toe anchors, they are there to keep that bottom cable tensioned against the slope. So you don't want to allow material to fall from behind. So if your slope is very irregular, you're going to need more toe anchors than not. So it is important to remember, okay, like if I have toe anchors, maybe cable anchors are going to be easier for frequent cleanups. But if I don't have frequent cleanups, I can use the thread bar. So that's how the procedure is done.
Yeah, nice comments on like some nuances in the design there. All right, well, that will conclude the technical part of this. I'll go ahead and say thanks again to Lucas and for everybody joining, and I'll turn it back over to Christina for some closing messages.
All right, thank you, Lucas. Great presentation. Thank you, Mark, for moderating this live stream. To all our viewers, thanks for the questions. Thanks for staying with us here today. If you like what you watch, please remember we have other live streams from Maccaferri. One coming up is on December 4th at 2 p.m. Eastern Time. We have Channel Erosion Protection Design Software with Anna Perez. Please sign up in our Eventbrite to get notifications. If you like what you watched today, remember, visit the Geo-Institute website. Remember, also like our YouTube page, follow, share, etc. Lucas, great presentation. Every time I learn so much about not just the products from Maccaferri, but how, so much design behind. When you are in the road, you're driving and you see those, something is holding the slope, but you don't know what's behind. So much thinking in there. Again, thank you. Thank you, Mark. Thank you, Luca. Everybody, all our viewers, thank you so much for being here, and see you in the next one.